This is section 9.1b, sequences and series. A recursive sequence is defined with its own previous terms. The first one or two terms are always given. Now, recursive sequences are a little bit hard to get used to because we're not used to defining things in their own terms or working backwards. So I'm just going to introduce you to this a little bit today. We won't be spending a lot of time on recursion or recursive sequences in this chapter, but you should just be introduced to it because sometimes in higher math you'll be using recursion. It's also used a lot in computer programming. So this is an example of a recursive sequence. You've got your first two terms given to you. And then you have the definition of the sequence, and as you can see, it's defined in terms of itself. So a sub k equals a sub k minus 2 plus a sub k minus 1, where k is greater than or equal to 2. So what does this look like if we fill it in with numbers? Well, it looks like this, and I think by looking at the numbers we can see where the definition comes from or why they write it in that way. So the first two terms are easy, those are given, 1, 1. And then we get into the terms that are defined by k. So a sub k, that's a sub 2. Notice that in this particular case, a sub 2 corresponds to the third term because the counting of terms started at 0. Sometimes that happens in sequences. A lot of times the counting begins at 1, but in this case it begins at 0. So in any case, a sub k, a sub 2 here for the third term, a sub 2 equals a sub 2 minus 2, which is a sub 0, plus a sub 2 minus 1, which is a sub 1. So as you can see from where the arrow is pointing, the cursor, this a sub k is a sub 2, and then I just use that same value of 2 and k, and then 2 minus 2 is 0, and then here 2 minus 1 is 1. So a sub 2 equals a sub 0 plus a sub 1. And as we can see that that means a sub 2 is equal to 1 plus 1, and that's why we get 2. Now look at the pattern. Look at the pattern of the following terms. Notice that 3 here is the sum of 2 and 1. Notice that 5 here is the sum of 2 and 3. Notice that 8 here is the sum of 3 and 5. 13, the sum of 5 and 8. 21, the sum of 8 and 13, and so on. So visually we can see that each term, once we get past a sub k, each term is defined in terms of its previous two. It's defining itself. And again, this is hard to get used to. Sometimes it's confusing at first. But this is just to introduce you to what recursion is and how a sequence can be defined recursively. This particular sequence is called the Fibonacci sequence. And the Fibonacci sequence is interesting because it actually appears in biology. It, for example, describes how trees branch. They start with one shoot, and then there's one branch off that shoot, and then the total number of branches at any one time can be given by the Fibonacci sequence. So it's kind of interesting, but it's a good way to at least introduce you to recursion. Another sequence that's defined recursively, which you've probably seen already, is the factorial sequence. So k factorial with that exclamation point. It's almost like you're yelling the k out. K! The k factorial equals k times quantity k minus 1 times quantity k minus 2, and so on all the way until you get to 1. And you've seen factorials before, so this little pyramid here on the lower left just shows you what the factorial terms look like. 0 factorial is 1, that's by definition. 1 factorial is 1, that's also by definition. And then from 2 factorial on, you can see that it's just the number times that number minus 1 until you get to 1. Okay, so 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. You can see the pattern repeated there. You just keep subtracting 1 and multiplying until you get to 1. Alright, so you've seen this before, but the 2 reasons why I'm bringing it up again. One is that we're going to use factorials a lot when we get to probability and permutations and combinations later on in this chapter. And the second reason to introduce it now is because this sequence can also be defined recursively. So if we define this sequence recursively, this is what it looks like. In this case, you're given 3 terms: a sub 0 equals 1, a sub 1 equals 1, a sub 2 equals 2. And then we have a sub k equals k times a sub k minus 1 times a sub k minus 2, all the way until you get to a sub 1. For example, for 3, which is the minimum k that we're going with here, k greater than or equal to 3, a sub 3 equals 3 times a sub 2, because 3 minus 1 is 2, and a sub 2 is 2, times a sub k minus 2, and a sub k minus 2 is a sub 1, because 3 minus 2 is 1. And in this case, a sub 1 coincides with the endpoint. And so the answer is simply 3 times 2 times 1. And as you can see from where the mouse arrow is circling, that matches right up with our definition of factorials. 3 times 2 times 1, because you start with a number and then you keep going down 1 until you get to 1. So again, you've seen factorials before, but what you probably haven't seen is this recursive definition of factorials. We'll do a little bit of recursion in the classwork. We probably won't see it much after today, but we will be using factorials again later on in this chapter. Just a quick note on factorials. Again, this is just something to keep in mind in case you're curious about it, or in case you ever wonder what type of precedence factorials have. They have the same rank in the order of operations as exponents. Okay, so in this example, I've got 2n factorial, and that's the same as 2 times quantity n factorial, which is just like with exponents, 2n squared equals 2 times quantity n squared. Again, this note is not necessarily essential to your classwork, but it is interesting, and you may want to write it down because it might come up in evaluating factorials. Some examples to illustrate this. Let's look at this sequence. Write the first 5 terms of the sequence. A sub n equals 2 to the n over n factorial, and start with n equals 0. So pause the video and get that on your own, and once you have those 5 terms, then you can resume and check your answer. So this is what you should have come up with. 1, 2, 2, 4/3, 2/3. And we get these numbers just by plugging in different values of n successively, starting with n equals 0. So a sub 0 equals 2 to the 0, which is 1, over 0 factorial, which is 1, and 1 divided by 1 is 1. A sub 1 equals 2 to the 1 over 1 factorial, and that's just 2 divided by 1, and that's 2, and so on. Alright, so you should have been able to come up with those terms. Here's another example. Simplify this expression 8 factorial divided by 2 factorial times 6 factorial. And if you look at this carefully, you'll probably recognize a pattern. Now, since this is your first time looking at this example, or trying to simplify factorial expressions. I'm going to walk you through this one, and you should be able to do the next ones on your own. Alright, so if we write out this entire expression without the exclamation points, you can see that according to the definition of factorials, this is what it equals. The numerator is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the denominator is quantity 2 times 1 times quantity 6 times 5 times 4 times 3 times 2 times 1. Alright, so that's just writing it all out. And if you look at it expanded this way, then you should be able to recognize that you can cancel. And you can cancel part of the numerator with part of the denominator. And of course, then you're just going to end up with 8 times 7 in the numerator and 2 times 1 in the denominator. And that, of course, gives you 56 divided by 2, which is 28. Alright, here's another example, and you should do this on your own. Pause the video, do it on your own. Remember that you're going to be canceling, similar to the above example, and see if you get the right answer. So resume when you get the answer. You should have come up with 2, and the method is the same. You're going to expand it and then cancel what you can. In this case, you can actually cancel the 2 factorial with the part of the 3 factorial. You can also cancel the 5 factorial with part of the 6 factorial, and so you can double cancel. But in any case, you should have ended up with 2. If you didn't end up with 2, then you'll need to try to do this over again, expanding and seeing what you can cancel. And a final example, and the reason this is a little different is because we're not talking about a specific number n here, but I want you to try to recognize a pattern. You need to think about it a little bit. You might see it right away, maybe it's easy for you, but if not, you need to look at it and see if you can find a pattern. So pause the video, try and do that on your own, and then resume when you have an answer or if you get stuck. The answer is n, and that becomes clear if, for example, we plug in a specific number into n. Let's say I plug in 100 for n. Well, the 100 factorial is 100 times 99 times 98 times 97 times 96 times 95. That almost sounds like that beer on the wall song. But anyway, the numerator would be 100 times 99, 98, 97, etc. And the denominator would be 99 times 98 times 97 times 96 times 95. So you can see that the numerator is very similar to the denominator. They're only off by 1. So you can cancel everything else except for what you're left with, and that will be the number you started with, which is n. Okay, so plugging in specific numbers for n can help illustrate this, or you can simply recognize the fact that if you cancel the n minus 1 factorial with the n factorial above, all you're going to end up with is n. Alright, so thinking about these things in general ways is sometimes hard. It's a skill you're going to need for the rest of the chapter. Just be patient, because sometimes when you do these things for the first time, they're hard, but you get used to them. Here's the classwork. Page 650, numbers 51, 53, 55, 57, 61, 63, 67, and 69. Please write those down, and we'll see you in class.